Okay, so my name is Michael Watson. I'm here to present on detecting malware in the cloud and basically some experiments that we've been doing in this area. So a little background just in case you're not aware. Cloud computing is really built on virtualization, so the sharing of hardware between multiple operating systems. They're composed of a number of interconnected hardware nodes which are each hosting a number of VMs, and the VMs themselves are hosting an operating system. This architecture of interconnected hardware nodes presents new vulnerabilities for malware to get into the system and exploit it, whilst also providing us with new opportunities for detecting that malware. So shared hardware is one situation that is not really understood. You can block it with software, but each VM has to access the same memory, so there's the potential for malware to also exploit that. The cloud provider potentially doesn't have direct access to the customer VMs, which means that you can't place a detection system on the VM itself. And potentially homogeneous VMs implies that if a worm were to be able to exploit a vulnerability in one VM, it can spread throughout the whole cloud. So from our point of view, we can place a single detection system on the cloud node. We have the opportunity to combine the network view with the end system view and also distribute our detection system across each node. Hypervisor is the software component that allows the sharing of hardware between virtual machines. The hypervisor we're using is Zen, and it has a privileged domain known as DOM0 that we can actually place our detection system in. The ability to observe VMs is enabled by introspection, which allows us to access the memory of each VM in the cloud node. And libvmi is the library that allows us to write applications to enable that. Utility is something that we use on top of libvmi in order to extract the data that we need for malware detection. So this is the spec of our testbed. Here the important points are libvmi volatility, and we also use TCP dump to extract information from the network, each virtual network interface of the VM. And here's just a schematic of that. We've written a number of Python scripts in order to automate the process of extracting features from the memory and from the network. So to test our system, we use Kelios, which is it's a Trojan that acts as a bot, as part of a botnet. The Kelios botnet was taken down, but this recent development in a new strain is what we're looking at. So the actual experiment lasted 60 minutes, and we used the first 20 minutes to gather data on normal system operations so that we can establish what is normal and what is not. And then the last 40 minutes are under the presence of malware. So here we can see the first 20 minutes is fairly normal. All the processes are from when we started the machine, but then we inject the malware and we can see new processes. And this process is actually Internet Explorer, which is started by the malware in order to retrieve a malicious web page. Here we can see derived features. So this was raw features. This is the virtual size of each process within the VM. But here we're deriving the number of processes based on our snapshots. And we can see that the malware kicks off a number of new processes when it executes. And here finally there's another derived process. This is the total of all the virtual memory that's used by the malware processors. And this anomaly is due to a single process consuming 2 gigabytes of data. So in conclusion, we can observe different aspects of the virtual machines from a single position in the cloud. Multiple VMs can be monitored, and we can observe both system level and network level properties. In the future, we want to investigate more malware strains. We'll expand to multiple hardware nodes and investigate VM migration and combining the two views into one detection system. Thank you.